It's a pleasure to introduce Kevin Tucker, who's going to talk to us about an introduction to singularities and mixed characteristics.
Okay. Welcome, everyone. Thanks for coming to my talk, and thanks to the organizers for the invitation to speak. It's an honor to be here. Building on Carl's talk from yesterday, today I'll talk more in depth about singularities and mixed characteristic. More precisely, I want to tell you how we can extend and build a framework for singularities and mixed characteristic that enhances the ones we have in characteristic 0 and positive characteristic. Right, so each framework and the different characteristics comes with its own dictionary of terms. So let's start by reviewing the dictionary of terms in characteristic 0. Among the central classes of singularities in complex algebraic geometry are KLT, rational, log canonical, and Dubois singularities. These are all defined by Hironaka's resolutions of singularities, and they come with a good heuristic as a result. So intuitively, worse singularities require more complicated resolutions. So roughly speaking, all of these are trying to measure how complicated a resolution is. All right, so the four classes fit nicely into the implication diagram I've listed here. So for example, Kawamata log terminal singularities are automatically rational. All right, I've listed all four up there for completeness, but today we're only really going to talk about the top row. All right, as mentioned yesterday, a normal complex variety X is rational if and only if it's Comacalli and the push forward of the canonical is the canonical for any resolution. So note that this isn't the original definition. It's really a criterion due to Kempf, and it in turn relies on vanishing on Grout-Riemenschneider. But it makes it easier to see the relationship with KLT singularities, which is really what I want to focus on today. So very roughly speaking, you want to take this push forward condition and twist it by minus k, minus the canonical divisor. Right, so KLT singularities asks that the push forward instead of the canonical, you would take the relative canonical, right? So this ky over x down here, right? So which is the canonical upstairs minus the pullback of the canonical downstairs, right? And asks that push forward always gives you back the structure sheaf. When omega x is a line bundle, or i.e. kx is Q Cartier, i.e. x is Gorenstein, you can actually do this twisting, and KLT and rational are the same. I've indicated that in my implication diagram with this dashed arrow up here up at the top. All right. Otherwise, the key point is that we can at least pull back kx to a resolution and make sense of all this, provided kx has a multiple that is Cartier, i.e. when x is Q Gorenstein. And for simplicity throughout the talk, I'm going to largely stick to Q Gorenstein. All right, so if you haven't seen Q Gorenstein or KLT before, that's fine. Don't worry about it. Just assume everything is Gorenstein or maybe even a complete intersection. The diagrams collapse, so there's really only two cases here, and everything's simpler in that case. Okay. Even if your variety is not KLT, the push forward of this relative canonical gives you the multiplier ideal sheaf J down here at the bottom, right? Which, like the Grout-Riemenschneider sheaf that Carl talked about yesterday, is associated with vanishing theorems. So the relative canonical push forward is associated with, say, natal vanishing. These multiplier ideals will come up again a bit later in the talk. All right, so next let me tell you a little bit about the dictionary of terms in positive characteristic instead. And again, as Carl mentioned yesterday, we no longer have resolutions of singularities. Of course, even if we did, they don't satisfy the same vanishing theorem, so that's not really going to help us. So the singularity classes here in positive characteristic are all defined using the Frobenius or p-th power map. Just for the experts in the audience, I'm always going to assume that the Frobenius map is a finite morphism. The four central classes here that mimic those from characteristic zero are F-regular, F-rational, F-pure, and F-injective singularities. And note that they fit into the same implication diagram that we had before in characteristic zero. All right, so I'll tell you a little bit about a couple of them. But first, let me remark that you can, there's a variant on how you can think of the Frobenius inclusion. All right, so instead of just looking at the p power map here, you can view Frobenius as the inclusion of R in its ring of p roots. All right, so this has the advantage of distinguishing between the source and target versions of R. Right, so, and it also helps clarify, helps with defining F purity. Right, so F purity, which is the same thing as local F splitting. I'm using the term F pure largely to avoid any confusion with the theory of global F splittings. So F purity asks that the Frobenius endomorphism splits, i.e. that there is a R module retraction back here from R1 over P back to R. So an R linear map from R1 over P back to R that sends 1 to 1, splits that inclusion. Right, so it's equivalent to check for F purity by looking at the iterates of Frobenius, right? So because Frobenius is an endomorphism, most of the techniques come down to iterating it as many times as you can, right? So if the larger iterates of Frobenius split, right? Of course, I can compose with the inclusions here to get a splitting of the first one of Frobenius. Okay. So as I said, so that's the first term that I've talked about, F pure on the diagram. I really want to focus on the strongest classes that I can inside of this talk. So I really want to talk a bit about F regular. Right, so very roughly speaking, F-regular singularities are a perturbation-friendly version of F-purity. All right, so with the same assumptions as on the previous slide, so R still a domain of characteristic P, right? What does F-regular mean? Well, F-regular asks that you have something a little bit stronger than an F-splitting. So it asks that if you look at the map from R to R1 over P to the E, that instead of sending 1 to 1, sends 1 to C to the 1 over P to the E, right? That map splits, right? And it really is a stronger condition again for the same reason we said before. So this is the Frobenius inclusion. Afterwards, then I do this multiplication by C1 over P to the E. If I have a splitting back here, then I can pre-compose with that multiplication map to get an F to the E splitting. All right, so I want to think about this as a small C perturbation, and the requirement is that these perturbed splittings exist along any non-zero element C in the ring, right? The idea here is that if E is really large, then 1 over P to the E is really close to 0. So C1 over P to the E is pretty close to 1. It's a very small perturbation, right? Similar perturbations will be important later on, even in mixed characteristic. And before I move on, let me also just say that just like in characteristic zero, where there was a heuristic for how you were measuring singularities, something similar can be said here. Classical theorem of Kuntz from the late 60s says that our Noetherian is regular if and only if Frobenius is flat. And that sort of motivates the study of singularities in positive characteristic by techniques that measure the failure of flatness, right? So given our assumptions, right, so then if I have a regular ring, flatness translates to saying that these modules R1 over P to the E are all free modules. And it's pretty easy to see then that for any non-zero element C, if I take big enough roots, what I'll get is part of a free basis for that free module and will split off. So in particular, regular rings are strongly F-regular. Okay. So, so we have the two dictionaries now. We have a list of singularities in characteristic zero and a corresponding list in characteristic P. We can already see that they're hopefully related. They satisfy the same implication diagrams, but to strengthen the correspondence, the basic idea here is to relate the two dictionaries. We do so by pairing them up via reduction modulo P. All right, so I don't want to spend too much time on this or make it too technical. So let me do this in a very simplified setting. right? So the following sort of a central result of Smith, Hara, Meta-Srinivas, Hara Watanabe in some forms, right? So if I look at an hypersurface singularity, integral hypersurface, the corresponding complex singularity is KLT if and only if when I reduce modulo P for all large P, what I get is F-regular, right? So this indicates how one would match up the singularities on the top left, the strongest singularities appearing on all of my diagrams, right? So as I said, I've stated this for the hypersurface case for simplicity, but this really holds quite a bit more generally, right? So let me remark, I don't want to lie a little bit too much. Everything's very nice in the top rows of my diagrams. The mod P correspondence is a bit more subtle / conjectural on the bottom row, but I'll leave you to look into that. And as you can already see from this, this correspondence, mixed characteristic lurks somewhere in the background, right? So it's very natural to ask about the singularities of rings like Z adjoin X mod F, okay? So without further ado, I'm sorry, I don't have the fancy PowerPoint capabilities that Carl has. So let's go ahead and pull back the curtain and welcome the mixed characteristic dictionary to center stage. Right. So, all right. So mixed characteristic really has started to blossom in the last decade. Many of the terms I've put here on the diagram didn't even exist 10 years ago. Note that the singularity classes fit into the same implication diagram. That's not a coincidence. It's a guiding principle that was used in their development. As an introduction to mixed singularities in this talk, I'm again largely going to focus on the strongest possible case. So everything what you see in this top left corner. All right. You see a slash there already. Note that there's some ambiguity where what you put down there. So this is still somewhat under development. What you put there kind of depends on what you want. All right. So we'll get to that ambiguity in time. Also, I'm again not going to say anything about the bottom row. And in particular, I'm not going to say anything about the word perfectoid showing up essentially anywhere in my talk, although those techniques underlie a lot of the advances. But I will tell you, if you want to hear more about that, you can go see Joe's talk later this week, Joe Waldron. All right, so before I go on to the next slide, let me also say a little bit more about my terminology for the rest of the talk. All right, so whenever I say mixed characteristic, it means I'm working a finite type over a nice local ring of mixed characteristic 0p, something like ZP, where the characteristic of the ring is 0, but the residue field characteristic is P. Whenever I say characteristic P, it means I'm working with rings or varieties, schemes of equal characteristic P, schemes over FP or FP bar or something like that, where everything in sight has characteristic P. And whenever I say characteristic 0, I mean I'm really working with rings that contain Q, right? So, and secretly, I'm largely thinking about complex varieties. Okay. All right, so we have, I'm trying to introduce this mixed characteristic dictionary to center stage here. All right, so without saying the names of any of the words yet, all right, so just like we did in earlier with the characteristic P and characteristic 0 dictionaries, in order to make that introduction, I have to say how we're going to pair things up. Right, so mixed characteristic lives in between characteristic 0 and characteristic P. So I put it in the middle. All right, so you get characteristic P by going modulo P, and you can get back to characteristic 0 by inverting P, right? And whatever we do with our dictionary should be compatible with both of those transitions in some way. All right, so and again, for this talk, I want to focus on KLT and F-regular, these strong classes of singularities. We already know this correspond by reduction. All right, so inverting P is something that looks a heck of a lot like a localization statement. And so any good class of singularities should be stable under localization, right? So singularities are really a local phenomenon. So, but this left direction, this variant of localization, means that whatever I put in here for box corresponding to KLT and F-regular, when I invert P, I expect to get KLT back, okay? On the other hand, if I go to the right for mixed characteristic, heading to the right, going mod P is like restricting to a hypersurface. And so the natural thing to do is to ask for variance of deformation or adjunction and inversion of adjunction properties to hold. All right, so let me say more about what I mean by that in the simplest case. Right, so sort of the general framework of adjunction, inversion of adjunction, deformation is the following. For simplicity, let's say that R is Gorenstein local, and I take a non-zero divisor. The expectation or the hope is that the quotient or the restriction R mod X has nice singularities, if and only if the pair R comma div X has nice singularities, right? So inversion of adjunction and adjunction in both directions, right? So now I'm not talking about pairs in this talk for simplicity, so I'm kind of trying to sweep that under the rug, maybe a little at the end. But what I want you to notice here is that this really is, again, a two-way street, right? So there's a back and forth that you could do if you introduce pairs. On the other hand, if I don't really care about the pairs, then the idea should be that I can just drop this divisor completely, and if R div X has nice singularities, then R2 has nice singularities. And the composite between the two, it gives me this deformation statement, right? So if R mod X has nice singularities, then R should have nice singularities. Again, R here was local, so if you were not working locally, you might want to say things like in a neighborhood of the divisor or something like that. Okay. So before I go any further, let me also just say my diagrams are meant to be schematics to give an idea. Don't get confused by my squig arrow over here with the mod P. I'm not saying that what I put in here when I go mod P should be F-regular. Of course, the deformation argument is saying the other direction, right? So whatever I put in here hopefully satisfies this adjunction, inversion of adjunction and deformation package. So when you're F-regular in positive characteristic, the mixed characteristic guy should be whatever you want to put in here for these nice singularities. Okay. All right. So I'll give you a couple of ways to fill in box as we go in further in the talk. But maybe before we do that, I want to give a little bit further motivation about the kinds of things you could do if you could fill in box. Right. So tell you why you might care about this a little bit more. Right, and so with that, let me give you the following application. It's a theorem of Ma and Schweid. That sort of refines the information we have about KLT and F-regular via reduction mod P. Right, so and what it says is that if you go mod P and you're F-regular for 1P, then you can lift that up, and what you get was KLT and characteristic 0. All right, and this is a particularly useful criterion. So contrasting it with what we had before, the usual rigmarole with reduction mod P would have told you that to check for KLT, you need to check something for all large P or some very, very large P, right? What this says is that if you find a single P, for which the reduction mod P is F-regular, then you win, and it gives you a good test for KLT. Since F singularities are highly computable, so you have criterions known as, say, Fetter's criterion or Glasperner's criterion to detect for F regularity, right? This gives you a very quick method to use Frobenius techniques to check for KLT singularities. Okay, so in order to prove the theorem, I'll sketch the idea really quick. All you need is some way of filling in box that satisfies the deformation and localization packages, right? So if you put in nice singularities in the box, right, then, well, and nice satisfied those two packages, the reduction mod P being F-regular would deform to give you that, well, ZP X mod F had these nice singularities. Then I could localize to get QPX mod F having KLT singularities, and you can then base change or switch from QP over to C if you like to get the full statement. Okay. All right. Right, so hopefully this helps to show that having some mixed characteristic way of filling these things in really informs and tells us a bit more about KLT and F-regular, which maybe you already care about a bit more. Right? Again, just as before, I've stated the hypersurface case for simplicity. In fact, the hypersurface case can be, I think, seen by work of Zhu from earlier work that doesn't use these methods. It also holds much more generally. So the Q-Gorenstein setting would work for Ma and Schwede's work. The non-Q-Gorenstein setting and some versions for F pure and log canonical are due to Sato and Takagi. Okay. All right, so at this point, I feel like I've hidden it for long enough, right? So let me tell you the first thing that we can use to fill in the box. Right, so the first thing I'm going to tell you about is that splinter is a class of singularities that can be used to fill in the box in mixed characteristic. Okay, so what is a splinter ring? Right, so these showed up a little bit in Carl's talk, but I'll give a more formal definition here. Right, so a splinter ring is a ring so that when you take any finite cover, right, so that corresponds to a modular finite extension, say R inside of S, say of domains, right, that thing splits. Right, so again, in the same sense that we had splittings for F purity or F splittings, right? So I'm asking that there's an R linear map from S back to R that splits that inclusion, okay? Splinters are always normal, right? It's pretty easy to see. So the splinter condition in particular should tell you that the normalization map splints, so which gives you normal, right? When you're in equal characteristic 0, so when Q is inside of R, in fact, splinter is the same thing as normal, right? So the field trace can be used to give you a splitting. So the field trace in general sends 1 not to 1, but to the degree of the extension. So as long as you're in characteristic 0 where that's a unit, you win. But splinters, on the other hand, are very characteristic dependent. So if you're not in equal characteristic 0, if you're in positive characteristic or mixed characteristic, then it's very easy to see that that equivalence doesn't work. So Carl mentioned one example in mixed characteristic in his talk yesterday. Right, so if I look at, say, the elliptic curve, from our elliptic curve x cubed plus y cubed plus z cubed, say with coefficients in the two adics, right? So it's easy to see that that's not a splinter. The finite cover given by the multiplication by 2 map on the elliptic curve will not split. In fact, has image inside the ideal generated by 2, which is not a unit. On the other hand, if I replace Z2 with F2, then the corresponding elliptic curve, again, is not a splinter, and that's pretty easy to check. The Frobenius does not split, so it's not F pure. Okay. It can be a little strange to think about randomly searching for splittings, right? But so let me give you a very concise way to check whether there exists a splitting, right? So note that an inclusion R inside of S splits if and only if, well, I can look at the set of all potential splittings, this HOM set, HOM SR, right? And just look at the evaluation at one map back to R, right? So, and that will check directly if there's a splitting by seeing if that map is surjective. Okay. All right, so again, I'm trying to tell you that splinters and mixed characteristic fill in my box, but I've told you a little bit about what splinters look like in characteristic 0. It'd be a shame not to tell you what they look like in positive characteristic as well. So to that end, note that if, again, R is Q-Gorenstein, that's in fact F-regular and splinter are the same, right? So this in positive characteristic gives me an alternative characterization of F-regular, at least in the Q-Gorenstein setting. Outside the Q-Gorenstein setting, this is not known, and in fact is a very big conjecture in positive characteristic commutative algebra. All right, so, all right, great. So, so again, here's the theorem, right? So that splinters satisfy this package, right? So splinters and mixed characteristic satisfy the deformation properties to give you something F-regular and characteristic P, and inverse to give you things that are KLT and characteristic 0. Right, so that's the first theorem on this slide. The second theorem on this slide, you may have heard it before under another name. It's now known as the direct summand theorem, formerly the direct summand conjecture, right? And also came up in Carl's talk, right? So first conjectured by Hochster in the 70s and checked in the equicharacteristic case, and then finally verified by André in the mixed characteristic case. It simply says that regular rings are splinters. And I want you to see sort of two things from that theorem, right? So the first is that just like we had heuristics for why you could measure singularities in a certain way in characteristic 0 and characteristic P, this direct summand theorem gives you some motivation for why the splinter condition should be thought of as measuring singularities in mixed characteristics. So there's a good heuristic there. And then the second thing is that, well, the statement is very simple, but the proof was very hard and took a very long time. So I want you to have the impression that proving things about splinters is very hard, right? So, okay. And the coming slides, so I will tell you a bit about both the localization and deformation adjunction packages for the splinter condition, right? So both of them, there are some good ideas underlying the proof. So maybe I'll start with this first one. Right, so and briefly, right, so the deformation and diversion of adjunction and adjunction package for splinters follows from vanishing theorems in much the same way that Carl spoke about yesterday, right? So rather than just rehashing that, let me give you the local version of the vanishing theorems that's at play here, right? So let's say R is a complete local domain and has fraction field K. I can look at the integral closure of R in an algebraic closure of its fraction field. That's called the absolute integral closure and generally denoted by R plus, right? And you can think of that as just being the composite, the union of all of the module finite extensions of R inside of this algebraic closure of the fraction field. All right. So asking that your ring is a splinter asks that all those S's split back to R. So maybe it's not that surprising, at least when R is complete, that R is a splinter if and only if the map from R to R plus in fact splits. Okay. So the big vanishing theorem that gives both of the theorems in some sense on the previous slide is the following, right? So it's due to Bott in mixed characteristic and Hochster-Kunicki in equal characteristic. Right, so this R plus, when considered as an R module, is a big Macaulay R module. Right, so there are some nuances here about exactly what that means. So let me just say the one maybe that's most relevant, I think, for Jakob tomorrow and easy to state here. So so what it says is that the local cohomology modules of this R plus vanish for I less than the dimension. All right, so, and of course, it's the maximal ideal times R plus is not equal to R plus. Right, so there are other variants on the big Macaulay condition. Right, namely, I could ask that I have things like a system of parameters for R that is a regular sequence on R plus, right? Or I could ask the same for all system of parameters. These notions all agree after completion, right? So if you prefer any of those descriptions, you can replace R plus here with its completion, or even in this case, it's p-adic completion, right? And mixed characteristic, and all of those will hold. Okay. All right, so that's all I want to say about deformation / adjunction for splinters. And so they follows in the framework that Carl discussed. Let me tell you a little bit more about the localization property. Right, so, and that follows again from some ideas that Carl introduced yesterday. Right, so I'm going to give you a way to think about splinter singularities and mixed characteristic using alterations. Right, so here, suppose X is a normal Q-Gorenstein in mixed characteristic, right? And I take a normal alteration pi from Y to X. So again, that just means essentially a blow up of a finite cover, right? So for any such, I get a trace map, right? So that relates the push forward of the canonical from the alteration mapping to the canonical, right, of my space X, right? In much the same way that we had this twisting by minus k to transition from rational singularities to KLT singularities, twisting this trace map also gives me a trace map from the relative canonical, right, back to R as well. Okay. Trace maps are functorial. So if you understand what trace maps look like for proper birational maps or blowups, as well as finite maps, then you understand them in all cases, right? So and you've seen them already in this talk, right? So for proper birational maps, the trace maps are just the natural inclusions, say pi lower star omega y and omega x, or twisted the push forward of this relative canonical as an ideal inside of R. When instead pi is finite, then this relative canonical, in fact, can be identified with the Hom set, Hom SR, that we saw before. And in the trace map is this evaluation at one map that can be used to check for splitting. Okay. So with that as a definition, let me introduce yet another player, right? So we say that X has plus regular singularities if the trace maps from the relative canonical back to the ring surject for all normal alterations. Okay, and again, sort of the mantra here is that combines some of the ideas used to define KLT or rational singularities in characteristic 0 with the ideas that were used to define splinters in mixed or positive characteristic. All right, so this definition here at the top of my screen is just repeated from the previous one. So the definition of plus regular is still up there, right? So the point here is that plus regularity really gives a way to unify all of the different singularities across our dictionary, right? So plus regular in characteristic 0 is the same thing as KLT. Again, maybe this is not so surprising. All of the finite covers already split, and so the resolutions capture all of the behavior that you might want to see. In mixed characteristic, right? So the theorem then would be that requiring splittings for finite maps or this condition for alterations are the same thing. And then again in characteristic P, F-regular, which we already saw was the same as splinter, in characteristic P was the same as this plus regular. So so the nice thing here is now I have a uniform definition, if you like, of all of these three different singularity classes, right? And it's really that uniform definition that allows for the localization statement, right? Because I have these surjections for all alterations, I can take one in mixed characteristic that dominates a resolution after I localize or invert P, and that will give you that plus regular or splinter singularities localized to give you something which is KLT. All right, so I've listed a bunch of names here on this slide. Probably the most relevant here for this are the earlier ones, right? Maybe I didn't say this earlier, but my conventions, since there are a lot of names in this talk, is that if I'm a co-author on the paper, then my co-authors will forgive me, so they only get letters, but everyone else gets names. Okay. But some of the others I haven't quite introduced their contributions yet. So one of the things that showed up a little bit in Carl's talk was the derived splinter condition. So Bott really showed that in mixed and in positive characteristics, splinter is the same as derived splinter, right? So it behaves this way. There is a subtle point here. So in characteristic 0, derived splinter by the work of Kovács is really the same as rational. So if you like, the subtle point here is that maybe derived splinter is not the right thing to fill in the dictionary because it doesn't correspond to both KLT and F-regular as we would hope. Okay. Yes. Okay. All right. So as we've seen now, all right, so I have one way to fill in the box. All right, so I mentioned there's some ambiguity maybe about how to do it. I also mentioned that proving things about splinters is annoyingly difficult, right? One of the reasons I want to introduce some other ways to fill in box is because there are some things we would like to know about splinters that we just still don't know, right? So once I fill in the dictionary, I also want to have a lot of the properties correspond as much as possible, right? So a question you could ask is, well, if I look at mixed characteristic splinters, are they stable under small perturbations in the same way that we went from F pure to F regular in characteristic P? Maybe another natural condition to ask is the splinter locus open? Right? And at this stage, we don't know the answers to either of these questions. So let me tell you about some solutions that will allow us to sort of get around that. Right? To that end, here is another option you could use to fill in box, and I'll say this with a theorem in a second, right? So it looks like a very complicated definition here, but to cover it very quickly, BCM-regular singularities are what you get by taking splinters and forcing them to be perturbation friendly, right? So instead of just asking that for all finite covers, R to S, the map splits, again, I want to ask that the map from 1 to a small perturbation, C to the epsilon splits, right, for all C and some small epsilon depending on C, right? So again, this is just a small C perturbation of the splittings from R to S. And you can write this down in terms of the trace maps as well. Again, so in terms of the trace map, this maybe looks even more like a small perturbation, right? So I'm looking at the relative canonical divisor and perturbing it by epsilon times the pullback of div C. Okay, and the request would be that those maps are all surjective. BCM-regular is really a stronger condition again than splinter in the same way as we had before. So if the map here splits, right, then I get an arrow this direction, and I can split the first part of that by composing with multiplication by C, right? Another way of phrasing the question of are splinters compatible with perturbations is just to ask, is the converse true? Note that the converse is okay in characteristic P for Q-Gorenstein, but if you remove Q-Gorenstein, it's again a big open question in positive characteristic. And again, the theorem here is that this is another way of filling in the box, right? So that this does fit into the same framework you could use in our dictionary. So BCM-regular singularities are slightly stronger than splinters possibly, right? But also satisfy the deformation and adjunction package to F-regular when I go mod P and localize to give me something KLT and characteristic 0. Of course, you can ask, why are they called BCM-regular singularities? BCM didn't show up anywhere, all right? So Ma and Schweid were the first ones to introduce them, and let me just relate it back to their initial definition, right? So what they really were looking at was take a complete local Q-Gorenstein mixed characteristic domain. Essentially, what the modern language would say is that your BCM regular in the sense I described earlier, if and only if you get a splitting from any perfectoid BCM R plus algebra, right? So as we saw before, the splinter condition asked that you split off of all of the, or that R splitted off of R plus, right? And we knew that R plus was big Macaulay. So you could ask that you get splittings off of bigger big Macaulay algebras, and that would lead you to what they were looking at when they first defined BCM regular. I noticed at this point in preparing my slides that I hadn't given many examples of just about anything. So I thought this would be a good break to say a couple of words to say that you really can write some of these singularities down at this point. So for instance, you could look at the Fermat hypersurface and mixed characteristic. So where I've replaced again one of the variables here by p, and assuming m is small with respect to the number of variables in some way, then what you get will be BCM-regular. In this instance, when I go mod p, what I get is F-regular. So then the inversion or the deformation package gives me that these rings are BCM-regular. You can push this a little bit more. I can actually do this with quality over here, but you have to be more careful with the adjunction. All right. Here's another example where that fails, or at least where going mod p doesn't quite give the same thing. So I've written down what is a D4 singularity in mixed characteristics. So again, look at a standard D4 equation and replace one of the variables by p. Right. So so those guys will all be BCM-regular. In fact, with co-authors, we checked that rational double points of mixed characteristic 0, p at least 5 are all BCM-regular by showing explicitly that they are direct summands of regular rings. And more generally, Q-Gorenstein direct summands of regular rings are always going to be BCM-regular, essentially relying on the direct summand theorem. You can generalize that a bit further, and I think this is important for Jakob's talk. In fact, all two-dimensional KLT singularities of mixed characteristics 0, p at least 5 are BCM-regular. And I think, as Carl mentioned, the analog of toric rings here, so log regular rings, all right, are BCM-regular, and this is really an analog of a result of Gabor-Romero. So I've got a couple more sort of big things to tell you about to finish off my talk. The first of which is I want to give you an application of, right, so we fixed the perturbation problem by introducing BCM-regular singularities, but I want to give an indication that once I've done that, this BCM class satisfies, again, a bunch of nice properties you might want to transport over from characteristic 0 or characteristic p. So you want to ask what other properties can I transport over? So I'm going to do that by giving an application to local fundamental groups. All right, so what is a local fundamental group? So here I'm really thinking geometrically. So take a complex algebraic variety x and pick a close point little x inside of there. The local fundamental group of that is the fundamental group of the link of the singularity. So take a small sphere of radius epsilon around your singularity and intersect with your variety. That gives me the link here. And then I want to take the fundamental group of that. And the idea here is that if the singularity is more complicated, the link will be worse. And then the fundamental group is probably going to be much bigger. All right, so another perspective on looking at and trying to measure how bad a singularity is. Okay, so it was first conjectured by Kolar and then later shown by, in the last 10 years, by Braun, that if you take a KLT singularity over the complex numbers, then the local fundamental group is finite. Prior to Braun's theorem, right, something a little bit weaker was shown by Braun, or was shown by Chen-Yang Xu, right? So namely that the profinite completion of this local fundamental group for a KLT singularity is finite. And one of the reasons Xu was able to do this is that while the actual fundamental group is a little hard to get your hands on algebrogeometrically, this profinite completion you can realize as the tau fundamental group of the punctured spectrum of the completion of the stalk at that point, right? So there's an algebraic formulation of this the profinite completion of the local fundamental group. All right, so so that was the story in characteristic 0. In characteristic p, all right, so we proved a similar theorem. So for F-regular singularities, right? So again, the analog of this local Latal fundamental group, all right, is finite for F-regular singularities in characteristic p. And in fact, it was shown by Bott, Gabor, and Olsen that the finiteness statements in characteristic p will give Xu's original theorem by reduction mod p. Okay, And the motivating theorem that I was trying to get to in mixed characteristic is just the statement that this package also works for BCM-regular singularities in mixed characteristic, right? So if I take a BCM-regular singularity in mixed characteristic, its local telephone matter group is finite, okay? You can generalize the ideas in this slide in many different directions. So one is to get a hold of finiteness or bounds on the torsion in the local class groups for all of these singularities, which I believe was featured in Zishuan's talk yesterday. You can also look at the telephonal groups of the regular locus of these singularities and get results that are analogous to those in characteristic 0 by Greb, Kebekis, and Petronel, as well as myself and the same co-authors plus a couple more in characteristic P. Right, so there's a lot more to do here. I'm not going to say anything about the techniques used to prove this theorem in mixed characteristic, but let me just say that all three of these theorems can be shown by sort of the same method. You find a invariant that scales appropriately by degree for a quasi-étale cover. In characteristic 0, that's the normalized volume. And positive characteristic, it's the F signature. And in mixed characteristic, we introduced an invariant called the perfectoid signature to do this, right? All three of them will give you some effective ways of actually doing the bounds as well. All right, so with what remains of my talk, I want to tell you a little bit about the analog of this multiplier ideal in mixed characteristic as well. And again, this relates back to the problem of the openness of the splinter locus, which I mentioned was open, right? So, in order to check that, you have to come up with an ideal that determines what the non-splinter locus is. So Q tau alt here, this showing up on this slide, right? So, so without asking that you're a plus regular or that you're a splinter, you could just look at and try to define an ideal measuring how far off you are from there by looking at the intersection of all the images of these trace maps from the relative canonicals for all normal alterations. All right, so the definition as I put it up here, it doesn't even reference the characteristic, so it's natural to ask what it gives you in characteristic 0 and characteristic P first before going to mixed characteristic. And a theorem of myself with Blickler and Schweid says that, well, again, in characteristic 0, maybe this is not surprising. The finite maps all split, so this tau alt gives you back the usual multiplier ideal we had before. In characteristic P, it gives you the test ideal, and I've made a slightly different tau here. This really is the test ideal coming from tight closure theory, which I'm not going to say anything about. So if you like, take this as a definition of that test ideal and use it as motivation to go learn about that somewhere else. But one of the key points in both settings is that this nasty intersection here at the top stabilizes in both settings, right? So for the characteristic 0 setting, to get at the multiplier ideal, we know we only need to look at resolutions of singularities. So you can, in fact, just look at any normal alteration that dominates a resolution of singularities, and that will give you something which stabilizes the intersection. And in characteristic P, right, the important result is that you can actually stabilize it for a particular finite map, though it's not so easy to say exactly what that map is, right? So in either case, for sufficiently large normal alterations, you certainly get this stabilization. So before really thinking too much about this in mixed characteristic, you kind of want to ask, does the same thing happen, right? So does tau alt stabilize? Does it really give me the image of this trace map for some normal alteration? It's a particularly important question, tied very closely with localization. So it's really only by having such a stabilization that I know I can get localization statements, because localization is not going to commute with that infinite intersection. And once I have that, I get a coherent ideal sheaf, which will determine the non-splinter locus or something like that. So I really hope the stabilization holds, but we don't know it at this stage. However, we do sort of almost know it. And again, Carl alluded that yesterday. Right, so if you take the definition of this tau alt and you perturb it again a little bit along the divisor of p, you get something that we know does stabilize, right? So, and in particular then satisfies, gives me a coherent ideal sheaf, as well as behaves very well with inverting p. So when I invert p, I'll get back the multiplier ideal on the nose. Okay. This is a very hard theorem again, depending on the p-adic Riemann-Hilbert correspondence of Bott and Lurie, right? I won't say much about it here, but if anything, right, it does say we're getting a little closer to understanding when this splinter locus is open. We at least know the p almost or p perturbed splinter locus is open as a result. Okay. So we've now perturbed along P, but kind of following the framework of the talk, I don't know that if I perturbed along P, I have done enough perturbation. Maybe you have to keep going, and you would like to be able to perturb along any direction, any Cauchy divisor you like. And that leads us to yet another variation on these test ideal or multiplier ideals, right? So if you ask for perturbations along arbitrary Cauchy divisors, the hope would be that eventually for all large perturbations, what you get is always the same, right? And in fact, that's the next theorem, right? So this is sort of a definition theorem, if you like, right? So for all large perturbations, in fact, you get the same thing. As Carl mentioned yesterday, it suffices to take a perturbation that it captures both the singular locus and the P fiber, right? And then once you've done that, it's unaffected by further perturbation along any other effective Cauchy divisor. Essentially, by definition, then, again, remember, BCM-regular was defined by asking for perturbation stability in all directions from the splinter condition. This gives you that this tau of R determines the non-BCM-regular locus. In particular, that locus is open. So while I don't know it for splinter, I do know it for BCM-regular. Right, so great. So we've got a very good theory now of, we've got some kind of a theory of test multiplier ideals and mixed characteristic, right? And again, if I go back to the sort of framework of the talk, I want to know exactly how does it relate when I go in the two directions to positive and mixed characteristic, positive and characteristic 0, right? I've said the first one at least already in a different context. So if I go to the left, I really hope that this multiplier ideal inverts to give me the test ideal or multiplier ideal, test ideal, they're all the same, right? So I hope I get the usual multiplier ideal in characteristic 0 when I invert P. For the other direction, the enhanced version of the deformation property would be to ask for restriction theorems, right? So here I want to know that the singularities only get worse when you restrict along a hypersurface, right? So that's a containment between the restriction of these test multiplier ideals and the test multiplier ideals when I go mod the equation of the hypersurface. And again, that should work in a given, for a given hypersurface in mixed characteristic, or for one when I switch characteristics, say to characteristic P, right? And in addition, this recovers sort of all of the other multiplier test ideals variants that were already previously introduced in mixed characteristics. So Carl mentioned one of them yesterday, namely tau B0. In Mon Schwede's earlier paper, they introduced another one, the BCM-B test ideal, if you will, right? So, and this new tau of R unifies the theories at least up to taking all small perturbations. So after a small perturbation, all of the things sort of agree. All right. As I said in this talk, I didn't talk much about pairs, although you can generalize essentially everything I said in this talk to pairs, and there are many good reasons to do that, right? So if you're talking about test and multiplier ideals, there are a lot of very well-known properties that you might want to move over to mixed characteristic, namely things like restriction theorems, we already said, transformation rules, Skoda, summation properties, subadditivity. Carl mentioned effective global generation and things like that. Right, so so you get all of those as part of this package with this new tau R. Okay. So here's my example. And so let me just also highlight that there are already some sort of maybe unexpected applications of this. So as an application of some of these properties, Feng, Gubler, and Kuhnemann were able to give some results on solutions of non-Archimedean Monge-Ampere equations and mixed characteristic relating to the previous lecture series, right? So I encourage you to take a look at that. All right, so that's really all I want to say for my talk here today. All right, so thanks for listening.
Anybody have a question for Kevin?
Could you please go to the local fundamental group slide?
Oh.
So the full force of Pollard's conjecture, we strongly favor this is not known.
I'm not sure I know how to formulate it. So I mean, I only really have, I'm not in a setting where I have a good version of the local fundamental group. So I just know how to algebraically define the local Littell fundamental group.
You have some heuristic for why the splinter condition is so nice in mixed and positive characteristic, but is in damping and characteristic 0?
Sort of, yes. So the point is that the because the maps all split in characteristic 0, it's not possible to get any unexpected vanishing theorems. All right. So another way of saying it is that finite covers are not that interesting in characteristic 0. All right.